Hey everybody, welcome to another exciting class in digital design. We've got a homework 10 coming up, and it's due on Monday. It's due on Monday. And there are two topics that are interesting. They come out of the book. The book calls it Finite State Machine Optimization. But optimization is different, can mean different things to different people. What they're really talking about is reducing the total number of states. And to them, minimizing the number of states is optimization. So as it happens, one of the things that we do in order to minimize the number of states is we engage in two different techniques. One is called row reduction, and the other is called implicant charts, and the book describes these both in some detail. And what I do is I start with the simplest first example. So we're given this sort of finite state machine. Right? Is it a Moore machine or is it a Mealy machine? What kind of machine is that? Anybody know? Correct. And why is that? Right, the outputs appear in the states. Right? So this says if you're in state B, you get 0. If you're in state C, you get 0. If you're in state D, you get a 1. So since the outputs are only a function of the state, then we say this is a synchronous machine. And as a result, because the outputs are only a function of the state, we say it is a Moore machine. If we saw outputs underneath the inputs with a slash, then we would call it a Mealy machine, because the outputs would be changed immediately upon input changes given the present state. And they would propagate their outputs before you transitioned all the way to the next state. There'd be kind of like a little race condition going on there. So that's the first machine that we're going to consider, and it's called a Moore machine. Is this a minimal machine? That's the basic question. Look at a machine like this, and the answer is you can't tell. You have to go through a procedure. Two procedures. We'll examine the first one, row reduction, and we'll see that this is indeed not a minimal machine. So let's have a look and see what we can do to take this machine and encode it into a present state, next state table. So what I have done is I've taken this machine and I've written it over in here. A, B, C, D are the different states. So I wrote rows A, B, C, and D. Under the next state, I determine if the input is 0 or 1. In fact, the input could be more than just 1 bit. It could be 2 bits, in which case I could have 4 columns in here if it's 2 bits. Or it could be 3 bits, in which case I could have 8 columns in here. It's too complicated. I don't want to deal with that now. Let's just do 1 bit, 4 states. Next state, here we are in A. If you get a 0, next state is A, and that's why I write A here. Here's the next state. If x is equal to 1, it's a B. So what I do is I start with A and I say next state's either A or B. And the output is going to be 0 or 0. Well, say if it's A, it's 0. In fact, what you do, since this is a Moore machine, what you could do is when you write down A, B, C, and D, you can go straight to the outputs and know that it's going to be output 0, 0, 0, and 1. 0, 0, 0, 1. You don't have to think about it anymore. Done. Then when you're in A, you either get a 0 or a 1, and your next state's either going to be A or B. If you're in D, you get either a 0 or a 1. Your next state's going to be A or B. Is that right? Sorry. you're in B, sorry about that. If you're in B, you get a 0 or a 1, and where does the 0 take you? Oh, 0 takes you to D, and a 1 takes you to C. That's good. Okay, just checking. If you're in state C, and you get a 0, next state is D, that's good. If you get a 1, next state is C, so that's good. If you're in state D, you get a 0, next state is A. If you get a 1, the next state is B, so AB. And that's how you get this present state, next state diagram. So that's all good. All well and good. There is a compelling argument that what you're really looking for is not equal states, but equivalent states. And we know the states are equivalent if given the same input and output. The state machine behaves the same way if it has more states than if it has less states, providing the states are equivalent. If it changes the behavior of the state machine, it's not equivalent. So we have to have identical state machine behavior before we can substitute our equivalent states. So one thing we know is states are not equivalent if their outputs are different. So row A cannot be equivalent to D because the output is different. B cannot be equivalent to D. C cannot be equivalent to D because outputs are different. But A might be equivalent to B, and A might be equivalent to C, and B might be equivalent to C. If the outputs are the same and the next states are the same, here B, next states are D and C, here C, next states are D and C, then we have a matching row. These give us equivalency between B and C. Once we have that, then we can remove row C, and everywhere we see a C, like over in here, we can write out B because B is equivalent to C. And so what we've done is we've cut out this part, and now the next state when B gets a 1 is going to be B, not C. Once you do that, once B transitions back to B, we should get identical behavior. We don't need C anymore. And if B gets a 0, it will transition to D. So we basically cut out a whole state and simplified our finite state machine. And what we get at the end is A with an output of 0, okay. B with an output of 0, C is gone, D with an output of 1, and if x is equal to 0, next state is going to be A. If x is equal to 0 when you're in B, next state is going to be D. If x is equal to 0 when you're in D, next state is going to be A. And if x is equal to 1 when you're in state A, next state will be B. And if x is equal to 1 when you're in state B, we stay in state B. And if x is equal to a 1 when you're in state D, you transition back to B. So it says here, if I get 1, 0, the output will be a 1. Over in here, if I get 1 and then 0, the output is a 1. The same behavior. What if I got 1, 1, 0? And the output should be a 1. So over here, what if I got 1, 1, 0? Sure enough, output is still a 1. So the behavior is the same because we found equivalent states, and yet this machine is not the same as that machine because this machine has been minimized and that machine has not. And because this machine has fewer states, it's cheaper and easier to implement. And that is the essence of finite state machine minimization. What do you think of that? Who got confused by this? Any? Sure, go ahead. Well, what we're really saying is that the output is a function only of the state, not of the input. So if you're in state D, the output is going to be a 1. No, it doesn't matter. In other words, I hear what you're saying. If instead of being left with A, B, D, you were left with A, C, D, you would get an equivalent machine. However, it is my custom, if you will, to remove the higher states and keep the lower states. And when you're looking for answers in the answer key, you don't want to try and get some sort of an ambiguous result, which might be equivalent. You want to get an answer key that matches. So take off the higher states, either higher in number or higher in letter, and then you'll be consistent with the way, I'll call it, you'll be consistent with my custom on how to do the minimization. And that's the way the book does it too. If you can remove the higher states, the higher letters, you go for that first. Work your way up from the bottom. That makes sense. Sure. Any other questions about this example? So, now that you've seen row reduction, which gives you minimization, I can now show you a trivial implicant chart. It will give you the same result, but it uses a different approach, one that will give you a guaranteed minimized state machine. Sometimes row reduction fails. Oops. Sometimes but implicant charts always work, assuming you do them properly. So the implicant chart, we start with the second letter, B, C, D, and then you start with the first letter going on the horizontal part, A, B, C, and you stop at the penultimate letter, the second to last letter. What this does is it gives you a lower triangular matrix. And the lower triangular matrix allows you to do comparisons that may be in fact needed. And what you want to do is trivially eliminate those comparisons which are between two different states that have different outputs. So A has a different output from D, so we can eliminate that. We don't have to do the comparison. B has a different output from D. C has a different output from D. All the rest we don't know about. But now we're down to comparing only 3 different state pairs, which is cool. So now we want to ask, is A equivalent to B? Well, it is if A is equivalent to D. But we know A is not equivalent to D because we got an X here on AD. Therefore, eliminate it. A cannot be equivalent to B. How about A and C? Well, A could be equivalent to C if A is equivalent to D, but again, we know it's not, so we can eliminate AC. What about B and C? Well, B is equivalent to C if D is equivalent to D, and it is, and if C is equivalent to C, and it is. Row matching would have discovered it, but now by going through the process of iteration, we can put a check marks in here, and we can say that B is equivalent to C, and that is how you use an implicant chart. Same result, but now you are using a technique which will always work, as opposed to row matching, which sometimes does not work. Sometimes it does not give you a truly minimal form. And that's kind of a big deal. Kind of a big deal. What do you think about implicant charts? Now keep in mind we're using the simplest possible example here. Any questions about that? Let's try another one. I like this. Very nice, sort of simple-ish examples. Let's try I don't want that. I want that. I want to do an example that's simpler. Nice simple example. Yeah. Do a nice simple example. So what we're going to do is let's do A, B, C, D, E, F, G. Okay. And what we'll have here, that'll be our present state. And then what we'll do for our next state is we'll have x equal 0 and x equal 1. And then we'll have an output, y. And then the output will be something like, well, let's do the first, let's do the A, B, let's see, B, A, D, D, A, A, A. So it'll be B, A, D, D, A, yes, sorry about that. And B, yeah, it's an A. I'm having a little trouble with my own handwriting. Isn't this terrible? Isn't this terrible? So then C, there. Let's see what we can do here. Yeah, you can kind of see why it's really hard to do this stuff on the iPad. So what we're going to do here is quickly scan and see if BC appears anywhere, AC appears anywhere, DC appears anywhere, DE, nope, AF, nope, BG, nope, nope, don't see any row reduction here. So it doesn't look like anything can happen, but let's try the implicant table. B, C, D, E, F, G. And now we'll go A through F. A, B, C, D, E, F. And then we'll do the lower triangular matrix. Now what we'll do is we'll eliminate those things which are obviously different. So A is different from D, because outputs are different. B is different from D. C is different from D. D is different from E, F, and G. And now I can do my bitwise, my piecewise comparisons, right? A and B are equivalent if A is equal to B, and if C is equal to C. So I say that A and B are equivalent, because we have a self-referential equivalency here. A and C are equivalent if B is equivalent to D, but it's not, because we see there's an X on B and D. A is equivalent to D if B is equivalent to D, but it's not, because we see there's an X on BD. A is equivalent to F if B is equal to B, and it is, and if G is equal to C. Well, we don't know about G and C, so let's explore that. G and C, G is equivalent to C if A is equivalent to D, but it's not. So G is not equivalent to C, and now we can go back to A and F. A is equivalent to F if B is equivalent to B, that's good, and if G is equivalent to C, and we know now that it is not, so now we can eliminate that one. We go to A and G. A is equivalent to G if A is equivalent to B, and it is. And also if C is equivalent to E, and we don't know about that one, so let's explore it. C is equivalent to E if A is equivalent to D, and it isn't. Therefore, C is not equivalent to E, and so we remove that from the equivalency. Now we go back to A and G. A is equivalent to G if A is equivalent to B, and it is, and if C is equivalent to E, and it isn't. So that is no longer equivalent, or it never was. B is equivalent to C if A is equivalent to D, and it is not, because we got an X there. And B is equivalent to E if A is equivalent to A, that's good, and if C is equivalent to F. We know about C and F, so let's go to C and F. C is equivalent to F if D is equivalent to B, and it isn't. So C is not equivalent to F, and now if we go to BE, B is equivalent to E if A is equivalent to A, and C is equivalent to F. C is not equivalent to F, so that's not equivalent. So then we go and trace down BF. BF is equivalent if A is equivalent to B, and it is, and if C is equivalent to G, but it isn't, so that's no good. And now let's try BG. B is equivalent to G if A is equivalent to A, and it is, and if C is equivalent to E, but it isn't. So now we go EF comparisons. A-B comparison is good. FG, we don't know. Let's look at the FG comparison. AB, that's good. GE, let's look at GE. GE, we don't know. Let's look at GE again. So A compared to A. So GE is equivalent if A is equal to A, that's good, and if E is equal to F. So I need EF. And then over in here, F is equivalent to G if I have A equivalent to B, it is, and if G is equivalent to E. So I can write, I need GE in here. So this is true if that's equivalent, and this is true if that's equivalent, so the two things are mutually equivalent. So E is equivalent to F, and F is equivalent to G, which means E is equivalent to F and G. So I can write E, F, G. Isn't that cool? And then E is equivalent to F, we know that. And so we had a little cluster of equivalents right in through here. Isn't that cool? So now, that allows us to go through and remove this row, G, remove that row, F, remove the row B. Everywhere you see a B, you write A. Write A in there if you weren't removing it. Everywhere you see F and G, you write E. So that becomes E. That becomes E. I think I did that already. Oh, here. That becomes E. And that's it. So you got rid of 3 rows. And that's how the implicant chart works. What do you think of that one? That was a good one. And it was done with a Moore machine. What do you think? Who got confused by that? I thought that was a nice, real nice example. Me personally. Wasn't that a good example? Yes, Professor Lyon, a very good example. Can we have another one, please? You betcha. I got a bazillion of them. So let's do one instead of with letters. Let's do one with numbers. Would that be all right? I guess that's all right. So we'll do this. Present state, and we'll count 0 through 6. 0, 1, 2, 3, 4, 5, and then 6. And then for next state, we'll have x equals 0 and x equal 1. And then we'll have an output. And what we'll do, I think, is we'll start with a box. Just to sort of keep things neat. Oops, so much for neat. Well, neatness counts. Believe it or not, neatness actually does help. Because I'm using graph paper, I have lines, which you don't really get with an iPad, you know? Although maybe there's a nice way to do that, I don't know. There's probably an app for that, right? So there. So now I've got my, oh, it's a little jostled, sorry about that. Let's see, 5 to 0. Um, 0, 1, 1, 0, 5, 1, 3, 1, 1, 0, 5, 1, 0, 5, 1, and 5, 4, 0. Well, right away I can tell 4 and 5 can be combined. But let's see what happens if we use our implicant chart. So we'll do this. We'll go number starting at 1, 2, 3, 4, 5, 6, and then we'll start with 0, 1, 2, 3, 4, and 5. And then we'll draw our lower triangular matrix. And then what we'll do is we'll do some output comparisons. Row 0 is different from 1, 2, 3, 4, and 5. Row 1 is different from row 6. Row 2 is different from row 6. Row 3 is different from row 6. Row 4 is different from row 6. Row 5 is different from row 6. So that's what I got so far. I compare 0 and 6, and I say, you know, 5 is equal to 5, but I don't know about 2 and 4. So let's compare 2 and 4. 2 is equal to 4 if 0 equals 0 and if 5 equals 5. So 2 is equal to 4, and as a result I can put in the check marks in here and I can say 2 is equivalent to 4. Now let's go back. 0 is equivalent to 6 if 5 equals 5 and 2 equals 4, so these are equivalent, therefore 0 is equivalent to 6. See how that works? It sort of makes sense to people? So here's 1 and 2. 1's equivalent to 2 if 0 equals 0, and if 5 is equivalent to 1. I don't know if 5 is equivalent to 1, so let's chase it down. 5 is equivalent to 1 if 0 is equivalent to 0, and 5 is equivalent to 1. So 5 is equivalent to 1. So that's good. And now I can go back and say, is 1 equivalent to 2? 1's equivalent to 2 if 5 is equivalent to 1. They are. And so now I have 1 is equivalent to 2. Since 5 is equivalent to 1, I can say that's equivalent to 2, which is now equivalent to 4, because 2 is equivalent to 4. So now I got 5 equals 1, 2, and 4. So that's cool. Got a lot of equivalency here. Let's do some more. 1 is equivalent to 3 if 0 is equivalent to 3, but it's not, so that doesn't work. 1 is equivalent to 4 if 0 is equivalent to 0, I like that, and if 1 is equivalent to 5, and indeed it is, therefore I get a check mark here, and 1 is equivalent to 4, and that's true. We saw that here, actually. Let's take 2 and 3. 2 is equivalent to 3 if 0 is equivalent to 3, and it's not. 2 is equivalent to 5 if 0 is equivalent to 0 and 5 is equivalent to 5, so yes, indeed it is. So we have 2 equivalent to 5 already, so that's all right. 3 is equivalent to 4 if 3 is equivalent to 0, and it isn't. 3 is equivalent to 5 if 3 is equivalent to 0, and it isn't. And 4 is equivalent to 5 if 0 is equal to 0, it is, and if 5 equals 5, and it is. So 4 equals 5, and it's sure enough that it says that here. So that's fine. So we've eliminated 1, 2, 3, 4 different rows. 4 rows. Any questions about this? By eliminating 4 rows, I mean we've eliminated 4 states. So instead of a 6-state machine, we're down to like a 2-state machine. Well, it's a 7-state machine, and we're down to a 3-state machine. I forgot 0. Any questions about what I've done here so far? Wasn't this fun? Yeah, 1 was equivalent to 2 because when we looked at row 1 and we looked at row 2, we wanted to know if 0 was equivalent to 0. We knew that it was. And we wanted to know if 1 was equivalent to 5. And we had a check mark there, so yes, indeed. 1 is equivalent to 2. And then the question is, why is 1 equivalent to 5? Well, 1's equivalent to 5 because 0 is equivalent to 0, and 1's equivalent to 5, so it's self-referential. So that's how that worked out. So if you were to, I guess, implement this thing, you would probably cross off 4. You would cross off 2. You would cross off 5. And the only thing you'd leave is 1. And everywhere you saw a reference to 5, 2, and 4 is you'd write in 1. So that would be in here. And here. And then, sorry for the yellow. I think the yellow is not doing us any favors. So let's change that. Well, that doesn't make life any easier, does it? I don't know. Maybe that's better. And I can cross this one out too. And now, what was the other one? Oh, 6. 0 is equivalent to 6, so I now can cross off 6. And in fact, we don't see 6 referred to in here, so we don't have to actually write anything. So by the time we're done, we got a 0 with output 0. We got a 1 with output 1. We got a 3 with output 1. Oops. We don't need any other states. And if you get a 0 or a 1, it looks like you're just going to stick there at 0. Oh, I'm sorry. You're going to transition to 1. Ah. Right. And now, if you're in state 1 and you get a 0, you get a transition to 0. And if you get a 1, you're going to transition to 1. And if you're in state 3 and you get a 0, you stay in state 3. And otherwise, it's kind of a silly state machine, I guess. Otherwise, you transition to 1. So that's a way to approach the problem. It's a nice, let's say, consistent way to get a minimal state machine. And so that's kind of an interesting idea. And it's new for the book. You've got to read the book to really appreciate this stuff. So I'm hoping that you're reading along. And so what I would do at this point is try. Let's see. We did this. Let's see. Here's homework 14. Homework 14 is interesting because what he's doing is now a mealy machine. And so the mealy machine, what we're going to do, I'll redo this to clean it up for you. Let's do that. I think it's better if I start with a clean sheet of paper. There. So what we'll do, this will be homework 10, number 14. So we got A, B, C, D, E, F, G. A, B, C, D, E, F, and G. That is our present state. And for our next state, we'll have x equals 0 and x equal 1. And for our output, this is going to be a mealy machine now. We'll have x equals 0 and x equal 1. And so what we'll do, I want to try and frame this nicely so that my lines will fit properly. So let's do that. I thought maybe if I start by drawing the boxes instead of trying to draw the boxes around my writing, it would keep the writing more neat. The end of that sentence is, and I hope. We'll see. So that's a, well, it's a neat box anyway. If nothing else. So now let's see. I want to make sure I got the present states and the next states correct. So this is going to be E, G, D, F, E, C, B, F, G, F, B, D, E, C, and it looks like it's going to be 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. Is that correct? This would be number, let me just get this right. This is number 14. And I'm going to go back and just take a look at the diagram again, because encoding the diagram is so important. If you don't do that right, it's a mess. Let me just make sure I got it. Yeah. Alright, so A, next state is going to be EG. That's right. B, next state is going to be DF. Yes. C, next state is going to be EC. EC. Did I? Yeah, it's my handwriting. Sorry about that. D, next state is going to be BF. Right? E, next state is going to be GF. That's right. B, let's see. F, next state is going to be BD. That's correct. And G, next state is going to be EC. Yep. So I think I got it right. And so you can follow along. You can probably see how I'm getting these things. Somebody asked, does it matter if you write EC01 or EC10? And the answer is yes, it does. It matters. It makes a big difference, because it's a question of whether the row outputs are going to be equivalent. And so then you write your implicant chart, and it's B, C, D, E, F, G. And you start on the first letter, A, B, C, D, E, F, and you end just before the last one, so that you end on the penultimate letter. Then you do your lower triangular matrix. And then you eliminate everything with different outputs. So A is different from C. Let's get those. A is different from C in its output. So we put an X in there. A is different from F and G. Right? B is different from C, F, and G. C is different from DE, D is different from FG, D is different from F and G, yes. E is different from F and G, and F is the same as G, so that's alright. So this is our starting point for our implicant chart. In terms of pairwise comparisons, what we can do is we can compare A and B. And A and B are equal if D and E are equal, but D and E we don't know about. And also if G and F are equal, G and F we don't know about. So let's start with G and F. G is equal to F if B equals E. We don't know about B and E. And if D is equal to C, well, that we know D is not equal to C because we've got an X. Since D is not equal to C, F is not equal to G. So we get an X over here. Let's go back to A and B. A and B are going to be equal if D is equal to E. I don't know about that one. And if F is equal to G, it's not. So B is not equal to A. So that's gone. We got A and D. Let's compare those. A is equal to D if B equals E. We don't know about that. And if F equals G. Well, that we know is not going to work. Therefore, A cannot be equal to D. Let's go A and E. A is equal to E if E equals G, and it doesn't. B is equal to D if B equals D, that's good, and if F equals F. Well, F equals F for sure. And B equals D is true if B equals D, so that's self-referential. Therefore, I have B equals D. They're equivalent. So that's cool. Now let's look at B and E. B and E are equivalent if D equals G. I got D and G with an X. Therefore, this is not equivalent. Next, CF is equivalent if B equals E. B does not equal E, so C does not equal F. C and G are equivalent if E equals E, that's good, and if C equals C. Hey, wait a minute. That's a gimme. Row matching could have found that. So C equals G. That's cool. And now I have C is equivalent to G. I like it. Now let's do another one. D is equivalent to E. If B is equivalent to G, it is not. And so now I have reduced the total number of states by 2. Right? And what I can do in here is I can go in and cross out G, and anywhere I see G, I can write in C. Moreover, I can cross out row D, and anywhere I see D, I can write in B. Isn't that cool? So now I should see if I can find this answer in my answer key. It should say A, B, C, E, F. And A, B, C, E, F is there, with next states EC, BF, EC, CF, BB. It worked. And so it looks like the answer to 14 is B. And so that's how you get that. What do you think? Cool, right? It's a nice technique. It'll give you minimized forms, and it's amenable to computer implementation, which means if you write your state machine and encode it so that Quartus can read it, perhaps in VHDL or Verilog, it will do this minimization for you. But it's much better for you guys to be able to do this by hand. And there will be questions like this on the final. So it's real important that you learn how to do it. Any questions about this so far? This is the really challenging part of Chapter 9, I think. I mean, this is perhaps one of the most challenging things in the book. This is finite state machine minimization. You can now that you've minimized the number of states, now you could go and implement this finite state machine. That's a different problem. Different problem. Minimizing the finite state machine is really good because it allows you to minimize the total number of circuits that you need in order to be able to come up with the problem. Also important, encoding the diagram into a present state next state table like this is a critical first step and a fruitful opportunity for bugs. And I've made mistakes on that before. And once you do something like, you write down 0 over here where it's supposed to be a 1, your answer is completely different. And you don't get minimizations. And it doesn't work. And it's a bummer. I mean, it's a serious bummer. So that's a, that's a solution for you. The answer is not important. What's important is learning how to get the answer. That's what's important. And so I give you the answer and show you how to get the answer, but your most important goal in seeing this is to learn how to get it for yourself. That's the most important thing. Is everybody kind of on board with this? I know it's fairly easy to, I guess, envision how you might go about just sort of playing with the blackboard answer keys or something like this, but don't do it. It's much better if you can learn how to do these things on your own. Let's see if we can do another homework. This is homework 16. This is homework, I'm sorry, homework 10, number 16. So let's go and start a fresh piece of paper and see how we can work that problem. And we're going to come back to this on Monday, so don't worry too much about that. But one thing I want to point out, and this is sort of important, and I don't know if you realize this, okay? I'm taking, this is my old school calendar. I do this every year. I set up a calendar and I go, look at this, okay? I just want you to see this, because this is important. Your homework is due on the 19th, right? Today is like the 15th, and herein lies the rub. Finals week. Check it out. Finals week. So you guys, you know, you don't have much semester left. And I want to give you guys 2 weeks before finals week to review your final. So what this means to you is that on the, I mean, this is my job, okay? My job is to make sure that by the 19th, you guys have a final that we can start to review. And that final is going to include topics from Chapter 9. So we have to take time to do that, because aside from your so-called reading days, this is like our last day of class, right there, May 6th. So if you're counting classes, right? And I don't mean to be too pedantic about the whole thing. This class is like done. We're practically over with this class. We've got like, I don't know, 17 minutes left or something. I don't know, maybe a little more. But you got 1, 2, 3, 4. You got 5 classes left. No, 5, 6. You got 6 classes left. Maybe. Oh no, that's not a class. That's reading days. You got 5 classes left. So that's it, right? And so at some level, I need those classes to review your final for you, or else you won't have enough time to review the final. So that's important, and that's why we're moving things along. And so you guys, if you're behind in your reading, got to catch up with the reading. Got to do it. If you haven't been, assiduous with doing your homeworks, got to do it. Got to do your homeworks, because this semester is going to end incredibly fast, and I just want you guys to have a heads up on that, so you're not caught by surprise. So let's do homework 10, number 16. Somebody in the last class said, "Oh, can we have more time for this homework because it's hard?" And I'm like, "No, I'm sorry. I mean, because I can't change the calendar. It is what it is. You guys need the time, right?" So let's look at 16. I'm going to bring up the the state transition diagram for 16 is a bit of a challenge. Let me see if I can get that. Yeah, this is always states. I can't redraw this diagram and work the problem in the allotted time. So I'm going to take a shortcut, and I am going to start by writing out the present state, next state table. So you'll have to forgive me for that. And then the output. And because the output is got the x equals 0, x equals 1 thing going on it, that means, what that means to you is this is now a Mealy machine. And we're going to have states, and this is a big one, right? A, B, C, D, E, F, G, H. I'm going to try and frame this in with some nice lines. almost looks nice. So let's see now. We got H, C, 1, 0, C, D, 0, 1, H, B, 0, 0. And you can check me, please do check me and keep me honest on this. Make sure everything is correct. 0, 0, C, F, 0, 1, F, G, 0, 0, G, C, 1, 0, A, C, 1, 0. And now we got to do the implicant chart. B, C, D, E, F, G, H, A, B, C, D, E, F, G. Make our little lower triangular matrix. And then what we're going to do is look for outputs that are different so we can see A is different from B, C, D, E, and F. Right? B is different from C and D, and B is different from F, G, and H. C is different from E, G, and H. D is different from E, G, and H. E is different from F, G, and H. F is different from G and H. And G might be the same as H. So we've eliminated a lot of comparisons. Right? That was pretty good, actually. So let's look at G and A. G compared with, A and G. Yeah, A compared with G is true if G is okay with H. We don't know. And it's true if C equals C. So let's look at G and H. G and H is true if G is equal to A. So this is interesting, right? Because A and G require GH. G and H requires AG. And so as a result, A is equivalent to G, which is equivalent to H. So A is equivalent to G is equivalent to H. So that's pretty cool, actually. And if A is equivalent to H, then that's good, and that's good. So we got a few check marks there. What about C and F? Well, if H was equivalent to F, and it's not, so that doesn't work. So C and F, that's no good. I skipped one. How about B and E? B and E is good if C is equivalent to F, but it's not. So that's no good. How about C and D? If H were equivalent to F, now we don't see that, so that's no good. What about D and F? D and F, F and F, that's good. G and H, they're good. So now it looks like D is equivalent to F. And so now we've gotten, let's go back to B and E. I think I might have missed one. B is equivalent to E, if C is equivalent to E, and if D is equivalent to F. Well, it is equivalent to F because we know about that. So that must mean B is equivalent to E. That's good. So B is equivalent to E. So now, where are we? Well, H, any reference to the H is replaced by A. Any reference to G is replaced by A. Any reference to F is replaced by D. Any reference to E is replaced by B. So if I see H over in here, this becomes A. If I see F over in here, that becomes D. I don't see any E's in here. And so now my state machine just got a whole bunch smaller. And so now if I go back to my answer key, I'm looking for an answer that's sort of like A, B. This is, which one is this now? This is number 16. Let's go to number 16. Wrong place. So I'm looking for something that says A, B, C, D, and it's looking an awful lot like A. It should say A, C, C, D, A, B, D, A. Yeah, this is working. I did it. Yeah, I did it. I get 100. Yeah, so this is A. So the answer is A, but the interesting thing is not the answer, right? Oh, here's the answer. It's A. That's it. That's all I don't need to know anything else. And that's not true. You actually have to know how to get this, not just the answer is A. Any questions? How am I doing here, kids? Everybody all right with this? It's hard, isn't it? Yes. That's correct. One, two, three, four. But what he's saying, choose the reduced state transition table that belongs to the new finite state machine. Use implication charts to get your answer. And so what we're doing is we're using the implication chart to get a new implication chart. We're using the present state next state table and an implication chart to get a new revised, minimized present state next state table. And that minimized machine, which is represented here, is essentially what we're looking for, and interestingly enough, is exactly the correct answer. Now, somebody before said, well, what would happen if I just took out A and just left G? You could do that, and it would be a correct answer. However, you would not find it in the answer key, because that's not how I roll. Okay, I take out the high letters first, and then I leave the low letters, right? So if you did that, if you didn't work from the bottom up, crossing out rows, you would not get the correct answer from the answer key. You would have a minimized machine, but you wouldn't find it in the answer. It's not in the answer key. So that's a critical technique for you guys. You got to start from the bottom and work your way up when you're doing your reductions, or else you won't find the answer. Which, the answer's not important. Grades are not important. Learning is important. But if you want good grades, you better do it this way, or else you're not going to get a correct answer. So how's that? Any questions about what I have done so far? I think I have 4 minutes and 45 seconds left. So I don't know how much I can do. 4 minutes and 45 seconds. I go really fast. I can talk fast. But really fast. Let me just review what we've done so far, just so that you can kind of get sort of a big picture overview of where we are in Chapter 9. So this is our last chapter. This is the last topic that we're going to cover in the course. We're not going to have time for any new material other than this. We're going to have the implicant charts, and the row reduction for our finite state minimization. Here's an interesting one. What happens if you look at 15 and he says, what does he say in 15? He says, given the state transition diagram, reduce the number of states using row matching. Well, what I've done is I've tied your hands behind your back and said, well, you can't use your state-of-the-art tools, right? Because row matching will not recognize the self-referential aspect that G is equivalent to H if H is equivalent to G. Row matching doesn't do that. Row matching only matches when the next states are equivalent and the outputs are equivalent. So since that doesn't happen, this doesn't give you a minimized version. So if you were to go through the exercise of using an implicant chart, you would find the minimum state transition table. However, it would not be the correct answer because what he's asking you to do is just use row matching. And if all you do is use row matching, you can't find the minimum state transition table as presented. And thus, you have to write none of the above. It's a trick question. You got to read it carefully. But here's the heads up. You know, if it just says use row matching only, what can you do? You can't find a minimum form, and you won't get any one of the forms that are shown. And therefore, it's a none of the above answer. So that's a kind of a heads up on some of these questions. Some of these questions are like that. I make no apologies. It's just the way they're written. Maybe I shouldn't have written it that way. I don't know. Life in the big city. All right, what do we got here? 5, 6. I got 6 minutes left. Shoot. I can't do this problem in 6 minutes, but what I can do is I can show you a string recognition engine that will recognize arbitrary bit strings no matter how complex, so provided you have sufficient time and energy to do it. And what it does is it says, look, if you know you're going to try and recognize a string, in this case we'll recognize the string 0, 1, and any number of ones after 0, 1, 1, 1, 1, 1, 1, 1, 1. Then what you do is you can output a 0 when you get your first 0, output a 1 when you get your next 1, and then if you keep getting 1s, you go back to S4. And otherwise, if you get a 0, you reset. So that's your reset up at the top. And in fact, you can envision how this B tree, this binary tree, can be expanded and made quite large. I mean, depending on the number of bits in your string, it's growing exponentially. And in fact, it's growing as an integral power of 2, where the power is the number of bits in the string. So if you want to recognize 8 bits, you're going to have 256 different nodes in your state machine. I mean, this is not an easy draw. However, if you then proceed to do row reduction or implicant tables, you can actually minimize the number of states in the machine and still do a proper bit string recognition. And you can recognize any one of a number of different strings that may occur. In the world of cryptography, it's very good if you have what's known as the crib. So in World War II, one thing they knew after a weather report was being sent, routine encrypted with the Enigma, is at the end of every weather report there was a crib that said Heil Hitler. You didn't need to know any German. All you needed to know was Heil Hitler. And if you could decode that string and come up with that Heil Hitler thing, then you'd say, yeah, I got the correct code for today's Enigma machine settings, and you would have been able to kick it out and say, yeah, we've got the right code and we can decode everything that was sent today. So there's a compelling argument that being able to search for the strings has good practical application. especially in something like cryptography. So there's a, I don't know if you guys have ever seen, the cryptography movies. There's one with Alan Turing, I forget what the name is. But he essentially went through and came up with a machine that would iterate through all the possible combinations and searched for the crib. And that was an electromechanical machine called a bomb, because it was ticking all the time, not because it was a bomb. Here's a bigger sort of string. This guy. This is some example. Let me see what I can do to find that. Yeah. That's number 22. So this guy is number 22. 22, homework, 10. Okay. So what happens with simple row matching is you can see row 14 is equal to row 13, which is equal to row 11, which is equal to row 9, which is equal to row 8, which is equal to row 7. I don't even need an implicant chart to see that row 7 is equal to row 36 and row... all the 0, 0, 0 things are all equal. You can lump them together as long as the outputs are the same. And you can write those together. So you can write, to do this. How much time do we have? 3 minutes? Okay, 3 minutes, and do it. Just talk fast. Right, that's gone. That's gone. 11 is gone. 9 is gone. Right? So those are gone, and they're all replaced by 8. So if I see S9, 11, 13, or 14, I can just write 8. So here's 9, 11, 13, and 14. And now I can go in here and I can write S8. Similarly, if I strike out 12 and leave behind 10, anywhere I see S12, I can write S10 and get an equivalent machine. And that's very convenient, right? I don't know if this is a minimal machine. Probably not. But one thing I can say is I just saved myself a whole bunch of comparisons by doing the row matching first. Now if I do the implicant chart, things ought to get a little bit easier. But wait a minute, what about S7? Did I leave off S7? S7 should be equivalent to S8. Right? So this is S7. So now I got another one I can remove, and if I keep going like this, I'm going to be pretty close to finishing homework 10, number 22. So I can probably get rid of S8, and anywhere I see an 8, I can now write 7. And so things just got a whole bunch easier because I removed 1, 2, 3, 4, 5. I've gotten rid of 6 states out of 14. I've basically simplified the interactions by half. So that gets you a head start now on problem 22, which I think is very good. So you've got that. And you've got your homework, and you've got a nice day and a nice weekend. So hope you enjoy the day. Stay safe. And thank you very much for your attentions.